Now that we have a functional form for the velocity distribution of particles in an ideal gas, I want to talk a little bit about what that looks like. What does that distribution look like? So remember that last time we found that the probability distribution, the Maxwell-Boltzmann distribution of probabilities, looks something like this. We've got a factor of 4 pi out front. We've got a factor that's due to the normalization constant that looks something like this, kBt raised to the 3 halves. We've got a v squared. We've got e to the minus mv squared over 2 kBt dv. So this is what our probability distribution looks like. So what we want to know is, what does this function look like if we were to graph it? And then we'll take a look at what sorts of things it might tell us about the dependence of velocity on different parameters. So let me carefully draw, if you will, a picture of this function. Now, a couple of things I want to look at. Okay, I'm graphing this function, p of v, versus velocity. All right, so at low velocities, okay, this stuff is just a constant, this stuff over here on the left-hand side. So I'm going to ignore it for the most part and focus on the part that looks like this. Okay, and I've just plugged in a letter here to represent all those other constants, but you get the idea. So this is the function that we're actually graphing. When v is small, let's say v is near 0, this exponent part is going to be e to the 0, which just equals 1. But this part over here is going to be equal to 0. So in fact, we're going to start at 0 when we draw this distribution. So it's going to grow from there because there's everything in this expression is a positive quantity. There's nothing in here that can become negative. We've got v squared for one thing, so those can't be negative, but also e to something is never going to be negative either. All right, so we've got this function like v squared. So at the beginning, it's going to look a little bit like a parabola, like it's going up like v squared. But eventually, the part that's going to take over is this part. Now what's going to happen here? Well, this thing has a shape. If we were just to graph that part of the function, it has a shape that looks like this, where it starts at some finite level, actually starts at 1, and then it gradually curves down. We're looking at half of a Gaussian is what this is. This is a Gaussian function. So we're multiplying this by a function that looks like this. So the net function is going to be sort of a compromise between those two, and we're going to see that it comes out like this, more or less. All right, so this is what our velocity distribution looks like. So what can we tell from this? Well, first of all, we can tell that 0 velocity really doesn't have any probability. All of these molecules are moving. But the ones that have low velocity, that are in this region here, are not especially probable. In other words, they're not going to be the ones that are most emphasized, in this distribution. But we are going to come over to ones where we have a most probable thing here at the top of this curve. I'll make it look a little smoother here. All right, so this is something we're going to call the most probable velocity. And it would basically be defined by the maximum in this probability density. All right, it turns out that this is not necessarily equal to the average velocity. The average velocity is going to be somewhere else on this curve, as is the root mean square velocity. Those are all going to represent different points on this curve, not necessarily all the same point. All right, as I mentioned, we also know that a sliver of this curve, so if I have a velocity v here, that the value or the probability of finding a molecule at that velocity is really dictated by a small segment that has a width of dv around that, and is then also told to us by the value of the function at that point. So that's what's going to tell us PV dV is going to tell us the probability of finding a molecule with a velocity within a certain range around that value. All right. Now, we have several parameters here that the molecule depends upon, and those parameters include the mass of the particles, the temperature of the particles. I think that's probably about it in this case. But we want to know how these velocities will vary with these. as a functional form. All right, well, let me first show you what this distribution might look like for different temperatures. So I've drawn this for one particular temperature. Okay, whenever you look at a distribution like this for the velocity distribution, this is for a particular temperature. A particular temperature. And only one temperature. If I were to graph this, say, at a different temperature, and let's say we're doing it at a lower temperature, what would that look like? Well, it turns out that it would grow faster here at the beginning. It would come up to a higher peak out here, and then it would decay faster out here. That would be the distribution for a lower temperature. If I were to graph the distribution at a higher temperature, it would go out like this. It would have a gentler rise from here. It would come out to here and then decay slower. All right, so what are we deducing from this? Well, at low temperatures, I'm going to favor smaller velocities. So let me go back to that color. So at low temperature, I'm going to have, generally speaking, smaller velocities. All right, since this curve is focused down here, I think we can tell that the average velocity is going to be shifted down to a lower value. The most probable velocity is certainly at a lower value than it was in our original curve. And we're not going to see very high probabilities for high velocities out here. So in effect, the molecules are going to have a narrower distribution. There's going to be smaller range of velocities that are sampled by the various molecules at this temperature, but we're still going to see molecules at lots of different velocities. All right, and even way out here in the at the high velocity end, there will be some molecules out at that end. They'll be very low probability, but there will be some out there. So in essence, all that's happening when we change the temperature is we're changing the emphasis of the distribution to favor lower velocities. But we're not eliminating any velocities, we're simply shifting the emphasis to lower velocities. What about the higher velocity end? So what happens when we go to the red curve now and we look at that? Well, again, our most probable velocity is going to be located over here, so it has shifted up. We're emphasizing now higher velocities. We can also see that even though there are still lots of molecules out here that have low velocity, they're somewhat de-emphasized. In fact, they're much lower probability here than they were in the low temperature distribution. So at high temperature, we're going to have larger velocities or higher velocities, and we're going to have a much broader distribution across the whole range of velocities. Okay, so we have a much broader range of velocities that are going to appreciably contribute to the population of the molecules at this temperature. Now, the averages, as I mentioned, are going to shift to larger velocities than they were for the lower temperatures. But one thing that is the same about all of these curves, and I haven't drawn it very well, it's not drawn to scale, but all of the curves have been normalized, and this normalization factor basically guarantees it. The area is equal to 1. And that's true of all three of these curves. So in effect, what's happened at the higher temperature is we're sampling a lot more velocities. At the low temperature, we're sampling many fewer velocities, but they're all telling us essentially the same general information about the behavior of the gas at these different temperatures. Now, the last thing I want to mention is the variation with mass. And it turns out I'm not going to draw any new curves on this, but if I have large mass, and if I can draw it here, large mass means slower velocity. And that makes sense, I think. So this curve out here, the purple curve, also corresponds to a larger mass. The Small mass is one that's going to sample a lot of velocities and faster velocities. So small mass will correspond to faster velocity. So the high temperature curve is one that looks a lot like the small mass curve. Small mass. So in fact, you'll sometimes find Maxwell-Boltzmann distributions plotted for the different noble gases, and helium is like the red curve, and krypton or xenon is like the purple curve. The heavier the mass, the narrower the distribution, the lower the velocities in general.